Welcome to The Explainer. Today we are tackling a huge topic for IGCSE chemistry, something you see every single day, changes of state.
Okay, let's start with a puzzle. You've definitely seen this happen, right? You put a pot of water on to boil, you can crank that stove up to full blast, but the thermometer will hit 100 degrees Celsius and just stay there. It refuses to get any hotter. So what is going on? Where's all that extra heat energy going? Stick around, because we are going to solve that mystery.
So here's our game plan. We'll kick things off with a particle dance party, then follow an ice cube's big journey. We'll figure out that mysterious temperature plateau, crunch some numbers to calculate the energy, and then see how this all plays out in the lab.
All right, first up, the particle dance party. Look, before we can talk about changing states, we've got to get a handle on what the states of matter actually are. And it all, and I mean all, comes down to the particles, how they're arranged and how they're moving. So let's stick with this dance party idea. Solids? That's like the start of the night. Everyone's packed in tight, kind of shuffling on the spot, vibrating but not really going anywhere. Then you have liquids. The DJ turns up the music a bit. People are still close, but now they can move around, slide past each other. And then gases. Oh boy, this is the mosh pit. Total chaos, particles are bouncing off the walls, flying everywhere with tons of space between them. Getting this difference is absolutely crucial for your IGCSE course.
Okay, so we've got the dance moves down. Now let's put it into action. Let's imagine we have a single ice cube, and we're going to follow its journey from a solid all the way to a gas, step by step.
Here's the #1 rule you have to remember. When you heat something, anything, you're not just making it hot. What you're really doing is pumping energy directly into its particles. So what do they do with all that new energy?
Well, they start moving faster, and that right there is what temperature actually is. It's not some vague idea of hotness. It's literally a measurement of how much those particles are moving around, their average kinetic energy. So you add heat, you add energy. The particles move faster, and the temperature goes up. Makes sense, right?
All right, let's get back to our hero, the ice cube. Imagine it's at, say, a chilly -10 degrees Celsius. We start adding heat. What happens? Those water molecules, all locked up in their crystal structure, start vibrating like crazy. They're shaking in place faster and faster. Their kinetic energy is going up. So guess what? The temperature is rising.
And then we hit 0 degrees Celsius, the melting point. The ice starts to turn into liquid water. This is it, our first change of state. But this is also where things get weird. Something really strange happens with the temperature right at this point.
Which brings us right to the heart of the puzzle, the mysterious plateau. If you were to plot this on a graph of temperature against time, you'd see the line climbing, and then suddenly it just goes completely flat.
This is the key takeaway. During a change of state, whether it's melting or boiling, the temperature does not change. It stays constant. So as our ice cube is turning into water, even though we are still blasting it with heat, the thermometer stays stuck at 0 degrees. And spoiler alert, the exact same thing happens at 100 degrees when that water starts to boil.
So let's think about this. We just said temperature is a measure of how fast particles are moving. And we can see the temperature isn't rising. That means the particles aren't moving any faster. So if we're still adding all this heat energy, where on earth is it going?
Okay, here's the big reveal. That energy isn't making the particles move faster. Instead, it's being used for a completely different job. It's being used to break the bonds that hold the particles together. Think of it like this. The energy is being used to unlock the cage, not to make the person inside run faster. It's all going into increasing their potential energy by weakening those forces of attraction, allowing them to change from a solid to a liquid.
So if you look at the whole journey from ice to steam, you get this really cool pattern. First, you heat the solid ice. The temperature goes up. That's a slope on your graph. Then you melt the solid. The temperature stays flat. That's a step. Then you heat the liquid water. Another slope up. Then you boil the liquid. Another flat step. Finally, you heat the gas, or steam, and the temperature goes up again. It's like a staircase. Slope, step, slope, step, slope.
Okay, we've got the why down. Now let's talk about the how much. We can actually put a number on the amount of energy it takes to heat things up on those sloping parts of our graph.
And the key idea here is something called specific heat capacity. It sounds complicated, but it's not. It's just the number that tells you how much energy you need to heat 1 kilogram of a substance by 1 degree Celsius. Some things, like metals, heat up really fast. They have a low specific heat capacity. Other things, like water, take ages to heat up because their specific heat capacity is really high. That's why your kettle takes so long to boil.
And this is the formula you'll need. It looks a bit scary, but it's super useful. The change in thermal energy, Q, is just the mass, M, times the specific heat capacity, C, times the change in temperature, T.
So let's quickly break that down. Delta Q, that triangle just means change in, is the heat energy you've added, and we measure that in joules. M is the mass, and make sure it's in kilograms. C is that special specific heat capacity number for whatever you're heating, and delta T is just the change in temperature, how much hotter it got.
Now, this isn't all just theory and graphs. You're actually going to investigate this for yourself in the lab.
Yeah, a really important practical for your IGCSE is figuring out the specific heat capacity of a material. You'll basically be doing exactly what we talked about. You'll measure the mass of something, you'll heat it up and measure the temperature change, and you'll figure out how much energy you put in. Then you just plug those numbers into the equation we just saw and rearrange it to find C. You get to be the scientist.
Okay, so let's end on one last question to really make you think. We figured out that it takes a ton of energy to break bonds when you melt or boil something, so what happens when you go the other way? When steam turns back into water or water freezes into ice, new bonds are being formed. What happens to all that energy that was stored up? Where does it go? It's the other side of the coin. Chew on that one.